Some people have tried another way. Okay, so what they will do is, so here is a scan register. So let us say we have brought in 0 1 0 0 0 0. Okay, so this is F and this is, let us say, A. So F was 0, A was 0 1, this is F, A B C D E. So these are my perspectives. So these are my D outputs, these are my Q inputs. I shifted V1 and I made F equal to 0, A equal to 0, B equal to 1, etc., etc. Now, in order to apply V2, I can try to just shift this guy. So A will go from 0 to 1, B will go from 1 to 0, C will remain 0, D will remain 0, E may remain 0, F will become 0. This may result in the transition being launched, and then we do a capture. So in other words, shift in V1, again apply another shift to activate V2, to bring in V2. Then do a fast capture. So this is V1. So we have been shifting then we do another shift to bring in V2. This is V1, this is V2, and then immediately we have to apply a at speed capture, at speed capture. So here the scan enable signal was high in order to shift, then it remains 0 for a very short time and comes back. So till the even V2 we are shifting only, okay, whereas in the previous one V2 was captured. See, the scan enable signal became 0 here itself, because we are going to do a capture in order to launch V2. So there is sufficient time for us to change scan enable back to logic 1. But in your I don't know what happened. Here it is. See here, even V2 is V1 was shifted in, then that This guy also was shifted in. Now suddenly, we have to do up speed capture. So the scan enable has to be transition really fast. Okay, so that is a challenge. Okay, so this method is called as launch of shift. What does it mean? V1 and V2 are both shifted in, no capture. So that is the idea of transition delay faults. So transition delay faults are required because there may be circuits which have a speed issue, possibly because vias are not properly formed, right? They have a high resistance, or whatever could be the reasons. So we apply the transition delay fault model and generate test vectors. We may follow either launch of capture or launch of shift. So these are two methods to apply a test for TDF. We can launch the transition by using the capture or by using shift. So this is there is no scan enable need not be super fast, whereas in launch of shift scan enable must be very fast, super fast. So at least this much you should remember about transition delay faults. I want everybody to understand what are path delay faults, why we have to test for speed tests. Okay, why do we do speed testing? Okay, we are beginning to make chips which are very high speed, right? We are creating chips which are like hundreds, thousands of megahertz, gigahertz, right? So as a result, it's important to do speed testing. And remember, we can also do binning. Okay, we can save some chips from being thrown, right? If it doesn't work at 1 gigahertz, see if it works at 990 megahertz or 980 megahertz, and see if there are some which will work at 1010 megahertz or 1020 megahertz. So that is the idea of your transition delay faults. Okay, so path delay faults would be ideal to practice, but since we cannot handle that many path delay faults, we try to simplify and use transition delay fault models. So to recap, so what are the types of tests we do? Single stucket faults, then we do bridge faults. So tests for bridge faults, then we do tests for transition delay faults. So that is a complexity. Okay, we may have many thousands of patterns for each of these cases. So that increases the test application time. And as you already know, if you increase the test application time, the cost of testing increases. Cost of testing increases. All right, so we'll stop here and continue from where we left off after we come back. Okay, welcome back. So let me summarize some of the things we have been discussing, right? So we looked at digital testing, and we introduced the idea of fault models. So the popular fault models are the Stuckett fault model, in particular we should discuss the single Stuckett fault model. Okay. So we assume that exactly one of the nodes in the circuit is either stuck at 0 or stuck at 1. Then bridge fault model. In other words, two wires have a short circuit, right? Again, we will assume that there are no other bit faults, only two wires are short circuited, no other faults. Then there is the path delay fault model, which we explained is hard to do, right? So too many paths to consider. So we try to do transition delay fault model. So here we assume that exactly one node has a slow to rise or slow to fall. So slow to fall. Okay. One node has a slow to rise or slow to fall. So the industry definitely practices the single Stuckett fault model, bridge fault model, transition delay fault model, right? Path delay fault model, some industries, what they do is they select what are called as critical paths. Okay. So select critical paths. So a path is critical, right, if it is most likely to fail. In other words, there is very little slack in that path. Okay. So let me explain that. So if there is a circuit, there is a D here, there is a Q here, there is a D here, and there is a Q here, something like this. Sorry. Okay. So this is the state. So there could be a path like this, there could be another path like this, there may be many such paths. Now, as I have explained, the launch edge, okay, so if I launch the if I capture the value into this D flip-flop, I have launched the transition. Okay, I have caused the Q to get captured. Okay, there is some delay after which the output will change, the Q value will change. It may change from 0 to 1 or 1 to 0. Then all these guys will also change, all the gates along the path will have some delay, and finally this path may change here. It may take some time before the output changes. So this Q value changed here, okay, and it is available at D somewhere here. That is what it means, because there is a delay here, and this is the setup time. Okay, the transition must happen before this. Okay, the Q must be ready. I'm sorry, D must be ready before this edge comes. Okay, so this is the launch edge. This edge will launch the D into Q, and then it will propagate, and it's available at D, and it should be available before setup time. So this is called slack. In this example, the output changed well in time. Okay, so there will be no problem. There may be another path which is something like this. This is the launch edge, capture edge. So clock to Q delay, then this is a setup delay. So imagine that it happens like this. That means it just changed just in time. Then there is no slack, slack is 0. That means even a little bit it cannot tolerate. Okay, whereas here it can tolerate this much variation in the delay. Okay, if the gates are slightly taking longer, etc., it can still tolerate. Whereas here the slack is 0. So those paths for which the slack is very little, 0, or let us say very close to 0, they are critical, because any small variation in the delay, they are going to fail. So you may want to identify such paths through what is called as timing analysis. Okay, and only do slow to rise and slow to fall, falls on these critical paths. Now select only critical paths and do it. So some industries may follow this method, right? So we have looked at these fault models so far. Okay, and I have explained the motivation for each of these. This has been a very age-old thing. I mean, it has been around from I think 1960s or so. Bridge fault model became popular in the 90s, right? And similarly, speed testing. So some people will refer to all of this as a speed testing. Some people will call it at speed testing. So here one vector is enough to launch it, I'm sorry, to sensitize the fault and to propagate it, and same is true in bridge fault, but here we need two vectors. Okay. And in scan methodology, there are two ways to apply those vectors V1 and V2. One is called launch of shift and the other is called launch of capture. So this is what we have seen so far. Okay. All right.